Hello, today we are going to introduce about the parameter magnet machine design for 12 slot and 10 poles motor. My name is Omar Sadiq Abu Farid. In this mini project we will use Opera 2D software to simulate the PM motor. Then the static analysis and rotating machine analysis is done through the mini project. First, I will introduce about the synchronous machine. Then we will look through the objective. Then we will look through the objective dimension of the half motor and half stator winding layer of 12 slot 10 poles PM motors. Results on the magnetic field distribution factor map, radial and tangential components of main air gap, flux density, cogging torque and three-phase back EMF. After that we will conclude the whole mini project. An electrical motor actually is the machine which used the electrical power to generate mechanical power. AC synchronous motor is one of the electric motor which is classified into hysteresis, pulseless DC, sine wave, stepper and reluctance motor. Then the stepper motor is categorized further into permanent motor, hybrid and variable reluctance. In the mini project we will only focusing on the permanent magnetic designing. Why we choose to use the permanent magnetic motor? Because permanent magnetic has a high accuracy, high efficiency and smooth torque and maintenance free.
Hello, my name is Nadir Isawat. Throughout this mini project, we aim to design a 12-slot 10-pole PM motor and to analyze the magnetic field distribution for 12-slot and 10-pole PM motor. The third one is to analyze the mean air gap, flux density of the 12-slot 10-pole PM motor. And lastly, to evaluate on the cogging torque and three-phase back EMF of the 12-slot 10-pole PM motor. So first, we need to do some mathematical modeling to obtain the stator outer radius, stator inner diameter, magnetic thickness, shaft radius, to tip height, to end height, stator yoke with slot area and slot depth for the slot and pole dimension. Then the half rotor and half stator of the 12-slot 10-pole PM motor is constructed using AutoCAD software. Also, we need to evaluate on the number of slot per phase, which is given by this, and the number of slot per coil, which is given by this. In this slide, the winding layout of the 12-slot 10-pole PM motor is shown, where the winding layout can be found out by determining the slot and pole pitch per coil first. Then only identify the magnetic motive force for the 12-slot 10-pole PM motor. After that, we need to choose 4 coils for each coil by having the 0 degree for phase A, 120 degree for phase B, and 240 degree for phase C. So, this is the result that we obtained through the static analysis for the Opera 2D simulation, where it shows the magnetic field distribution for 12-slot 10-pole PM motor with the line distributed and color zone distributed. We can see that the magnetic pulling force for the 12-slot 10-pole PM motor is balanced or equal at the left or right hand side of the PR motor. From the colored zone magnetic field distribution, the highest magnetic flux distribution is only 1.51 Tesla, which is lower than the near saturation point, which is about 1.65 Tesla. This means that the 12 slot tempo PR motor can work under the mean point saturation of the magnetic field. Thank you.
Hello, I'm Batsin Liu, so I'm going to introduce on this vector map. This one is the vector map where the arrow entering the permanent magnet is the south pole, and then leaving the permanent magnet is the north pole. Here, this one is the enlargement of the 12 slot 10 poles motor at this pole, where we can see that this light blue region is the south poles and dark blue regions indicates the north pole region. Then moving to this graph, the left hand side is a graph showing the radial component of the mid-air gap flux density, where the highest positive value of the radial component happens in the north poles and the lowest radial components occur at the south poles. The sudden drop in the curve at the tip of the sinusoidal wave is due to the slotting effect. Meanwhile, the right-hand side indicates the tangential component of the mid-air gap flux density, where the ripples in the graph is due to the harmonics in the permanent magnet motor. Moving to the graph of the cogging torque versus the rotor positions, where the left-hand side shows the rotor positions from 1 to 360 rotor electrical degree, and then right-hand side shows the rotor positions from 0 to 60 electrical degree. We can observe that there is some torque ripples. Here, the torque ripples happen here in the 15 degrees and then 45 degrees due to the slotting effect. At this angle, it is the angle for the slot opening. Therefore, the sinusoidal waveform is distorted at this angle due to the existence of the air gap, which causes the noise and vibration. Lastly, the three-phase back EMF graph is presented in this slide. We can see that these three different phases is 120 degrees out of phase from each other. The back EMF will present when the magnetic field interacts with the electric field in the stator. This back EMF is related to the performance of the permanent magnet motor, where low ripples in the back EMF indicates higher performance in the permanent magnet motor. As a conclusion, through this mini project, we have successfully designed a 12-slot 10-poles permanent motor by mathematical modeling. Then, we also have achieved, through this mini project, we also have achieved the magnetic field distributions is generated using the Opera 2D to depict the balanced magnetic pulling force in 12-slot 10-poles permanent magnet. Also, the effect of the mid-air gap is evaluated from the radial and tangential components through the Opera 2D simulations. And lastly, we have demonstrated the cogging torque and the three-phase back EMF to show their relationship with the slotting effect.